Hello, everyone. Welcome to the Cihan topology seminar. Today's speaker is Chung-Ping Lai. He's going to tell us about discrete Morse theory. Okay.
Okay. So thank you everyone for joining my talk. So as introduced, this talk is more or less will contain like a brief introduction of discrete Morse theory. But to not do the theory disservice, I will just preempt and say my focus will mainly be on reducing some kind of operation that can be colloquially understand as reducing the size of a complex. So that would be my focus. But I hope it should still contain like a lot of like basic ideas of what discrete Morse theory is about. Okay, so for my motivation, so for my motivation, so because of where the field I come from, like I do some computer computations. So like simplicial complex is like basically the default default choice of computing topology, doing topology in computer science, in many computational applications, and which is but the problem with like having such a structure is that like a simplicial complex can have like often have like many simplices. For example, like a torus, I think has like at minimum like 20 simplices if you do like simplicial triangulation. And comparatively, if we use something like a CW complex, often uses like a decomposition that is like a lot more efficient. So at least for me, like one pretty big motivation is you to reduce the size of like the number of cells or simplices, whatever choice you prefer, and we just reduce the number, which is a pretty useful feature. If we are able to do so, that would be pretty useful for computation purpose. So how does the theory goes, right? So okay, so the discrete Morse theory is like developed by Forman, and when he built he built it on CW complexes, but the idea is really good at it. You can really generalize like many of the ideas to like many different kind of like combinatorial spaces. So the one that the combinatorial basis, like the choice of space that I use will be like a framework developed by Tucker, and it's some form of like abstract cell complex theory. And this approach is, and I choose it because I feel like that does what I want the best, like in terms of like reducing, like cutting down the size of the complex. And this approach is developed by Mr. Kao and Nanda, and they were the one who developed like such a approach to like reformulate the discrete Morse theory, and as far as I know, and this will be the approach that I'm sharing with you today. So we start by defining the abstract cell defining an abstract cell complex. So we start with a ring R, and as abstract cell complex, here I use like X and B. So it has like two components. One is like a graded set X, and we grade it with like integers. It's like graded with dimension. Essentially, we grade it with dimensions. And and for all internal purpose, we generally use like positive. We only consider like non-zero dimensions. And then we have this function that is like B, which maps two cells, like two given cells to an element in the ring R. And so and then we have so we have like two conditions which will be spoiler. So condition one is sort of like restricts the like this boundary incidence function. Like it will it will become clear over this. Hopefully, it becomes more clear in this like presentation why B is like called a boundary incidence function. But for the two conditions of this definition, the essential the essential spirit of the two conditions. For condition one is like it indicates that this boundary incidence is like about some kind of phase relation, or some may prefer a more accurate term like a phasic relation, where you have a phase relation and the difference in dimension is like one and one only. You can't have like we don't have like phases that are many dimensions apart. So that's something we take away. And then for the second condition, it's computational definition. And what this definition essentially says is, it essentially says it's like a feature about many of the chain complexes of this, we associate to the many of the combinatorial structure, where you have this like double boundary of boundary equals 0. That's really what this is about. The second condition is about. So we will go over that part as well. So that's really what condition 2 is about. There's like some partial D equals to, right? So okay, I will just write it out really quickly. So there's like some, right? So there is this condition that you see a lot, and that's really what that is about. And okay, so but that's the definition for now. Let's move on to the next slide. Okay, so now we are like putting in a bit more substance here. So like ideas about the definition. So firstly, we have this phase relation, which I use this arrow like this sign to denote. So we say beta and alpha, like they are basically they are elements of like an XB. Is a phase of alpha when the boundary incidence between alpha and beta is non-zero. So in essence, and we have like a stronger phase.
Okay, I think the one of your devices just disconnected, right? Okay.
Yeah. So I think it's back, right? So so I think that's somewhere here. Yeah. Yes. Well, yeah. Okay, I'm glad the disruption is not too long. Okay, so where am I? So there's like this phase relation, right? So there's this phase relation, where you want so if the boundary incidence is non-zero, then we say beta is a phase of alpha. And if also be careful, for the boundary incidence function, the order matters a lot. So it's like alpha beta, not beta alpha. So if beta is a phase of alpha, like the boundary incidence is non-zero. So like that means that really describes the boundary incidence a bit, right? When beta is a phase of alpha, the boundary incidence like says alpha and beta touches each other. And then for the regular phase, this is a bound. That means the boundary incidence number. And we say beta is a regular phase of alpha, and we have a notation for that as well. And then we have this idea of a subcomplex, which is x prime b is the subcomplex of xb if x prime is a subset of x. And there's a lot of writing there, but it basically says that dimension is you have the same dimension. Cells have the same dimension in either spaces, and you also have and you also contain, and also the subcomplex should contain all the phases of its cells, which is what a subcomplex, what everyone expects from a subcomplex, right? And it should be noted here that so this is an unfortunate feature of the boundary incident, like of this framework, this framework of abstract cell complex, is that morphisms between complexes are difficult to define. So so that's bad news if we want to apply tools in category theory, I think. So and okay, and then now this is a combinatorial space. So simplicial complex has simplicial chain complex, CW complex has cellular chain complex, and this abstract cell complex also have its chain complex. So quickly go through what a chain complex is. So a chain complex is a sequence of R modules, like we choose a ring R to be a ring, and then an R module morphisms. So you have this sequence, and when they compose, when you compose the differentials, you get 0 for at every dimension. And then when you have a chain complex like this, we have homology groups as defined by kernel mod image. So these are rather standard stuffs, except we do specify we want an R coefficient here. So these are standard stuff. And for our abstract cell complex, we can associate a chain complex to it using the boundary function. So the chain groups are the free R module generated by the D cells of the abstract cell complex. And then the boundary maps will be, or the differentials will be defined using the boundary incidence. So and this is where the boundary incidence is the most clearly useful. So you just add up the boundary incidence times the phases. And I hope in this process, like the abstract cell complex thing that I introduced, start looking familiar to the different kind of combinatorial spaces that you may have seen before. And the next slide is and as it turns out, but why am I using like this abstract cell complex idea? Well, that's because even though I'm like defining the cell complex and then its chain complex, I think intuitively, the better way to understand it is to really to think it the other way. That you have like a chain complex first, like be it your simplicial chain complex or your cellular chain complex, and then you end up having and then from that you get an abstract cell complex out of it. And we can see this from this proposition. So basically, if you have any chain complex of finitely generated free R modules, which simplicial chain complexes, CW chain complex, cellular chain complexes for CW complexes, or like the chain complex you do for simplicial sets, all of them like all those chain complexes are finitely generated 3R modules. And you really using that, we can define an abstract cell complex out of it, with like a little bit of algebraic trick, which is you have a pairing. Like you can say on an R module, after you have chosen the basis, you can define a pairing, which maps, which is sort of like an inner product, but which is basically an inner product. And then you can use like the inner product in conjunction with the differential map, the chain map, to define the boundary. So I mean, we can see it here. So right, to like we can see the definition here. So like we basically use the inner product in conjunction with the differential to define the boundary incidence. And I hope, yeah. So and then for this abstract cell complex that you obtain, that will be a chain complex that is basically the same as what you get. Well, basically the associate chain complex to this like abstract cell complex that we construct will be the same as the original chain complex. So okay, we move on to the next. Let me see. Let me move on to the. Let me try to move on to the next slide. Okay, I see. That's why it didn't work. Okay, so let's so can you see the change? I think the slide haven't been changed. Okay, so now the slide. Okay, so the slide had changed. Yes. So let's do two examples on what this abstract cell complex, some of this abstract, how to get an abstract cell complex directly from the simplicial complex, etc. So for an abstract simplicial complex, you have you basically have a set of vertex. In this case, I use S, and then you have like some collection of simplices. And then to define an abstract cell complex out of it, we basically take the set of simplices as our cells, and then we use the boundary incidence will be you just make a simplex, and then like you compute the and then you look at like simplex, and then you look at like all the subsets of the simplex that is like one cardinality, that is like one cardinality lower, and then you just like remove each element, and then you look at the and then you assign plus or minus to it. Oh, and yes, and before you do that, you need to assign an ordering on the vertices, like for the simplicial complex. For the simplicial set, it's slightly more straightforward. You can just define. You take the simplices as the cells, at the D simplices as the D cells. The boundary, and then the boundary incidence will be some sum of plus and minus one. For a simplicial complex, like the boundary incidence will be either plus one or negative one. For simplicial sets, we are slightly more flexible, so we have to add them up, so you get some numbers that are more interesting, I would suppose. And I guess I guess this is also a good place to mention some idea laying in the background, in that the boundary incidence is rather highly dependent on orientations. So because an abstract simplicial complex does not have like some inherent orientation. So we have to like do this extra step of like assigning orientations, which for simplicial complex we have the easy way to do it, which is to order all the vertices first. But for simplicial sets, things are a lot better oriented. So we skip over the orientation step, and we basically get basically the abstract cell complex is canonical. And I mentioned CW complex a lot, like earlier. So I should really tell you how CW complex generalize. But I decide against it because while you can really define the boundary, like the idea of like a boundary instance is like really well defined for a CW complex. But to like really define it is like a bit too much work. So I will refrain from doing that in this talk. But you can do the same for CW complex. I have it, and then it's more or less how you construct the cellular chain complex, really. So I will refrain from like just mentioning. So and then we do a quick example
I
here.
have a question about previous slide. What is the summation running over in the simplicial set case?
Oh,
Is it
oh,
the
the simplicial. Oh, that's the let me move back to the previous slide. Oh, that's the I. So like because like simplicial sets like indexes every individual phases. So you have to so if so I'm like looking at, so for sigma and tau, I'm looking at which di maps which of the phase map maps sigma to tau, and then that phase map comes with an index, and then the incidence number would be like -1 -1 to the power of that index. So you have like 0, so you have +1 -1 +1 -1 +1 -1 for the simplicial set case. Yeah, and then you add them all up because you are like adding up the boundary incidence. So it's like sometimes you add to 0 and sometimes you add to like 2. That both can happen, right? Because that depends on that. In that case, it means like the phase touches the co-phase touches the phase like more than once. Sometimes they touch them all in the same orientation, and sometimes they reverse orientation, which cancels out the number. So and we look at, and then the boundary incidence is like the sum of this like boundary, like this separate instance of boundary incidence, I would just say, if that makes sense.
Yeah.
Yeah.
Thanks.
And for the simplicial sets, that's where the unit, like the regular phase thing, like matters a bit. I mean, you will, yeah, because we are talking about this, I guess it's like good to mention. If you apply the regular phase for the abstract cell complex, it's like probably a bit more general than the regular phase definition you will see for many complex. So that's not something we will go, that's not something that is, I guess, super essential to this talk. So I will just refrain from like discussing it further. But the important thing is that for simplicial complex, like every phase is a regular phase. But for structures like a simplicial set, then you start seeing like irregular phases because your boundary incidents are no longer -1 or 1. You get 0, 2, 3, depending on what complex you have. Okay, so and just to give you a quick example of this abstract cell complex, the slides are not moving very quickly, unfortunately. Yes, okay, so now it works. Okay, so now the slides show up. Okay, so here we have like, I mean, I'm using like a simple 2 simplex to like demonstrate the abstract cell complex. So you see that for this simplicial complex, I oriented all the simplices, and then so you have like 3 vertices, 3 edges, and 1 face, and then So for the alpha to the 3 betas, I'm using the right-hand rule. So when alpha is like oriented upward, as demonstrated by the purple arrow, like the right-hand rule will indicate that you want some kind of counterclockwise. You want some kind of counterclockwise on the boundary, and that's exactly how the exactly how I happen to orient the edges as well. So in that case, like all the boundary incidents of alpha beta 1, alpha beta 2, alpha beta 2, 3, all the boundary incidents are just 1 because you are going through, you fit the orientation. And then, but for the orientation between the edge and the vertex, then we have like a little more variety. Okay, so yes, next week. Okay, and now we can start. So the slides are moving. So let me see. Yeah, that's unfortunate. It's can you see the slides? This can you okay? The slides are changing now. Oh, this is yeah. This works a lot worse than I expected. So okay. Yeah. This yeah. Yeah. Sorry. Okay. Okay. I'm going to use. Okay, I will use less. Yeah, I'll just use the. I will just share it with the other computer. Yeah, I'm really sorry. Unfortunately it doesn't work as well as I hope. So now, okay, I'm going to do it this way. Okay, so yeah, so that now I can write, but hopefully this is smoother. Okay, so now we talk about discrete Morse theory. So really quickly go through the backgrounds. So the discrete Morse theory is really inspired by the smooth Morse theory, which essentially studies critical points of smooth manifold to real number functions. And I won't go too much onto that, but here, obviously, because we are dealing with combinatorial spaces, we don't have smooth functions. So instead, we replace the smooth functions by functions that maps the cells to the real number or the simplices. And even though we say real number here, really we are just going to use integers as the outputs because we are operating in a fully discrete world. But the critical points, we actually have like correspondence, which are the critical cells. So theorem. Okay, so we start with a theorem. So this theorem is called the Morse inequalities. I don't know. It seems like a pretty big theorem in smooth Morse theory from what from the some of the things I heard of. But for us, okay, I'm sticking with like the CW complex version, just to make sure that because just to make sure that I'm not like overstepping some weird things. But for a CW complex and a fixed CW decomposition, the most important inequality for today's work is the first inequality, which says the number of D cells of a CW decomposition should be greater than or equal to the Betty number. And that's important because that basically gives a lower bound in terms of like how small we can go for a cell decomposition that we want to do. So the CD has to be greater than or equal to BD. So that gives us some context in terms of what we want to do. So, but obviously, most of the time you probably have a decomposition that is a lot larger than your Betti number. So that means that also means from the other perspective, we can say we have a lot of room to optimize the thing. And then the second and the third will be, I think, mostly for interest. And the chi of x in the middle of the second equation, that's the Euler characteristic of the CW complex. But so okay, next we want to define a discrete Morse function. So we have to do some setup first. So firstly, I will just like quickly introduce, like give some idea of what this function is. So let X be ordered by the phase relation. We are coming back to the abstract cell complex, the world of abstract cell complex. But you can really modify this to your favorite combinatorial space. So like the cell, any cells of your combinatorial space are basically ordered by phase relations, whereas the real number is ordered by the less than or equal sign. So the idea of a discrete Morse function is that it is a locally order preserving function with some exception. So we want the function to at least locally preserve the order that I just mentioned to you. So how does that work? Well, we have like a way to like rigorously quantify it, which is like this UF beta and LF beta. And the basic idea, the idea here is that the UF beta counts the number of order reversing cophase, which cophase of a particular cell beta here, whereas the LF beta counts the number of order reversing phases of beta. So what does it mean by order reversing? Well, basically, beta is a phase. Alpha is a cophase of beta, or in other words, beta is a phase of alpha. But F beta is greater than or equal to F alpha, whereas gamma is a phase of beta, but F gamma is greater than or equal to F beta. So we can basically, looking at the way the arrows is pointing, we see the order is reversed, and that's the idea. Okay, so now we can like rigorously define this discrete Morse function. So a discrete Morse function is a function that maps a function from the cells of X of the abstract cell complex to real number, such that for every cell beta, we have the following two conditions. Firstly, LF beta and UF beta have to be both less than or equal to 1. That means if beta beta can have at most one order reversing cophase and at most one order reversing phase. And secondly, if this order reversing does happen, so beta is a phase of alpha, but F beta is greater than or equal to alpha, then we require beta to be a regular phase of alpha. So if we do have like order reversing, we want this phase relation to be regular, which in our context means the boundary incidence is a unit. And now we also have this critical cell that we mentioned, which is a beta of X is a critical cell if it has no order reversing phases or order reversing cophases. So UF beta and LF beta are both 0 for a critical cell beta. So just a quick example in terms of what I mean here. So on the left hand side is a discrete Morse function. So roughly from the higher the dimension of the cell, locally the higher the number it is assigned to it. So the vertices are 1, 3, 5, the edges are 2, 4, 6, and the face is like 7. You may notice that the vertex, there's like a vertex 3 that is vertex with output 3 is a face of an edge of output 2. So there's some order reversing happening here. So there's some order reversing happening here, but that's fine because that's only one order reversing. So we don't have too much order, like we accept some order reversing, just not too much. So that's like not too many order reversing happening on the left. But on the right would be something that is not some function that is not a discrete Morse function. Because in this case, we do have like too many order reversing, like 5 to we can all see because I mean it's in like the function on the right is like intentionally made so that all the vertices have like all the highest value. So that like on the right hand side, that's like too much order reversing. And then I want to introduce a lemma about discrete Morse function. So let xb be a cell complex and f be a discrete Morse function. Now for a cell of x, turns out that either UF beta or LF beta, one of the two has to be 0. That means if it has an order reversing cophase, it cannot have an order reversing phase, and vice versa. And I will just quickly prove this lemma because I think it reveals something that is useful in the next session, which is assume otherwise that we have this like gamma beta alpha such that we have like a fully ordered reversing relation. Then by some definition of the condition on the boundary incidence function, there will be a different cell beta prime. That is also an intermediate, phase between gamma and alpha. And because we already limit like the number of order reversing phase relation to be 1 for alpha and gamma, really, then that essentially restricts it so that we have like this f gamma so gamma, beta prime, and alpha must be order preserving all the way. And then if we combine this with the first condition, we basically get a cycle of strict inequalities and then for that involves f alpha and f gamma, which would not make sense. So it's like you can draw a cycle of values that is like that with like some strict inequality, and I feel like this lemma is like really enlightening about the idea that I'm going to use from discrete Morse theory, which is like you don't want some like cycle of values to happen, and indeed this is the cycle that is something we want to avoid. And now, instead of all the discrete Morse function, now I really come to what I'm going to use from the discrete Morse theory. So this is I call acyclic partial matching, which is really discrete, like another side of a discrete Morse function, and it's actually what I really want to use. So it has a different name by Forman called the discrete vector field, and you can, but instead of like using like discrete Morse function definition, I would just define it as like a partial matching with a cyclic property. So which I will define. But really, it's like the same idea as a discrete Morse function because every discrete Morse function induces its discrete vector field, aka an acyclic partial matching. But every acyclic partial matching is also the discrete vector field of some discrete Morse function. I won't prove this, but that's so really it's like the two sides of the same coin. So I will define partial matching first. So what is a partial matching on XB? So basically, it's like a partition of X into 3 subsets, A, Q, and K. And Q and K really comes in pairs. And Q and K really come in pairs which is signified by the existence of a bijective function W from Q to K. And moreover, this function for every cell Q in this Q. So Q is like a regular phase of WQ of the output. So it's like Q and K are really like many pairs of cells which are related by a regular phase relation. And that's like where the matching comes from. So you're like really matching elements in Q, matching cells in Q to cells in K. So you can really think about every Q and K as like a lot of pairs and they come together. And for partial matching, there's like we can further define a idea called gradient, which is between cells in Q. And beta prime. So for cells, beta prime and beta in Q, we say beta prime is less than beta, or just less than beta, if beta prime is a phase of the W beta. So it's a phase of W beta. And recall that like W beta is a regular co-phase of beta. So it's a bit of up and down. So it's like really easier to see in practice, like in an example again. So here on the left-hand side, that's an example of a partial matching, where I'm using pink arrows to show what I'm writing is like I'm using pink arrows to denote W. So there are like two matchings here, which is gamma 1. So Q contains gamma 1 and gamma 3, whereas K contains beta 1 and beta 2. And then W maps gamma W, the pink arrows maps gamma 1 to beta 2 and maps gamma 3 to beta 1. So that's like you're like taking away pairs of cells at the same time. And then A is the rest of the cells. And I guess and also, but take it how you want, but the cells in A are actually the critical cell, corresponds to the critical cells of the discrete Morse functions. But they are the cells that are left behind. And also this partial matching here that I construct right here actually corresponds to the discrete Morse function that we see earlier. I won't go too much into how they are related, but the matching essentially happens when where the matching essentially happens where the order reversing actions happen on a discrete Morse function. So that's a partial matching, and then yes, and then this is the gradients. So I'm explaining so now I'm talking. So for this partial matching, what are the gradients on it? So I repeated the definition here. But here the only gradient here is that gamma 3 is less than gamma 1 because W of gamma 1, which is beta 2, is a cophase of gamma 3. So you can see gamma 1 is mapped by the pink arrow to the, I guess I'll just draw it out better. So gamma 1 is like being mapped to beta 2, and beta 2 is a cophase of gamma 3. So I hope you like see where the gradient is like coming from. So okay, next. So so acyclicity. So next we can define acyclicity. And acyclicity really means we don't want to have cycle of gradients. So on the left-hand side was the partial matching that I showed you. Then there are no cycle of gradients. But on the right-hand side, I constructed another partial matching. Again, I use pink arrow to denote it. And I hope it's you can see why. Yeah, I will be brief. I won't go through the technicalities, but I hope you see why you have like a cycle of gradients, which is the acyclicity that we want to avoid. Okay, next we can define the Morse complex, which is the reduction part that I mentioned earlier. So firstly, we have to like define this. We have to go through like many technicalities. Okay, which I mean, the construction of it will go through many technicalities, but I will just try to like convey the idea without going through all the algebra. So firstly, we need to define an idea called a gradient path. Like after we have an acyclic partial matching, we want to define the idea of a gradient path. And a gradient path is like really a sequence of elements in Q, and then you put like some alpha and beta. You put some cells of A at the beginning and the end of it, and then in the middle it will be like many cells from Q, like for partial matching. Like recall that we partition the cells into A, Q, and K. So like we put the critical cells at the beginning and at the end, and then we fill the middle with like cells in Q. And then the order relation in between the sequence is like precisely the gradient that we define. So those are the gradient paths, and for each gradient path we also have like a multiplicity, which is another giant equation which I won't explain. But I guess the only thing that is like perhaps worth mentioning a bit is that notes that we are doing division here. We are doing some division in this like giant equation, and this and because we are like using ring as like notation, so not every element of a ring can be divided. But here, if we take a note, it would be the boundary incidence between WQ and a Q, which should always be a unit. So that would be the only thing interesting that I want to mention about this giant equation. But we are still going to do an example to demonstrate the idea. So we can see, so again, back to the partial matching we had. So here really we have, and then I want to look at the gradient path from beta 3 to alpha 2, which are like two critical cells. So actually there are like two gradient paths. So one is like a small blue gradient path here, because beta 3 is a cophase of gamma 2. So there are like no Q in the middle, but that counts as a gradient path because you still somehow have a sequence that satisfies what we want. So that's like the first gradient path, which are used in blue arrows. And then there's like a brown gradient path, which has a more interesting journey that goes from beta, which goes from beta 3 to gamma 1, as the brown path indicates, because of a cophase relation. And then the matching maps gamma 1 to, and then the gradient, I should say gradient. So the gradient maps gamma 1 to gamma 3. I mean, if we look at the definition, it also goes through beta 2 in a sense. But ultimately, gamma 3 is mapped to beta 1, and beta 1 is a cophase of gamma 2. So we have like another gradient path, beta 3 to gamma 2, but it goes through the other side. So that's like how gradient paths looks like. And then the last thing that is like probably not obvious for the definition is that alpha has to be one dimension higher than beta. But it is part of the definition. It's just not very obvious, I guess. Okay, and then with the gradient path defined, we can define the Morse complex, which so because we are defining abstract cell complexes, so we just need the cells and the boundary incidence function. The cells of a Morse complex is precisely A, which are the, as I mentioned earlier, the critical cells of the acyclic partial matching. Where the boundary incidence function, that's a whole world that I'm probably that I better not go into, I guess. But it's just the sum of the multiplicities. But I think on a graph, you get some really nice graph. You get a really nice graph to see how this Morse complex is constructed, because you actually get the same space as we originally have, but we are like kind of like stretching all the cells a bit. So you can see the two gradient paths. We are seeing two gradient paths on this Morse complex precisely. So one is a blue gradient path, and then the really long brown gradient path on the other side. And in a sense, these gradient paths like help us like define the boundary incidence. That's why they are That's why we have to. That's why their multiplicity is part of the definition. So I guess, yeah, and that's like some demonstration of this Morse complex. And finally, we have the theorem, which is when you do this, you do preserve
Sorry,
homology.
may I ask something here?
Yes.
In the previous
Yes.
picture, previous picture, so the Morse complex is not a simplicial complex, is it? Or
No.
maybe I
No,
missed.
it's not a simplicial complex. Yeah, the simplicial, unfortunately, like yes, that's like an unfortunate part of this, which was why Forman really did most of his work on CW complexes, which is another really fluid combinatorial combinatorial spaces. So it's like simplicial complex are like very rigid, which means really many discrete Morse theory. Like if you are doing complex reduction using this kind of like approach, this like constructing this Morse complex, you almost certainly are going to break the simplicial complex structure of a simplicial complex. Yeah, because I guess it's true. I should like mention it here because it's a good place to mention it, because for this Morse complex, if you look at like how Forman and many people like treated it, it's really at its core, it's really more algebraic processing. It's like the Morse complex is like more like a Morse chain complex. And that is, so it's like you're cutting down, you are constructing a new chain complex out of the space you are given. So the geometric side of it is actually a bit more secondary, even though it can provide some cool images and cool intuitions. So the geometry, so the yeah the yeah if you basically if you want to do a more topological or geometric approach to this Morse complex, it is a bit more like the theory, as far as I know, is like less complete here, because this Morse complex is actually more like a more of an algebraic construction about a lot of like algebra ideas rather than so. Yeah, and if you try to realize this Morse complex, geometrically realize this Morse complex, it's a bit you do have a bit you do run into troubles in some way. So you not troubles, but like things become a bit more complicated. Like put it this way. And then, but for for but we do know at least even though other topological properties are probably a bit like, so I mean the homotopy equivalence could be a bit more dicey in terms of like how they are being preserved. Like that's where the complications is. But at least we do know when we do something like this, like reducing a abstract cell complex or whatever complex of our choice, when we reduce it to a Morse complex, we do preserve the homology. And that's and you can see that's like say this is the main theorem of the talk. And before I end, I won't prove the entire theorem, but I do want to like really quickly share at least some idea of how the theorem is like being proved for those who may find it interesting. Basically, what you do is like you knock out, like, because Q and K are matched, right? So it's the idea is like you pick an element Q in Q, and then you also look at WQ. Then you really remove them from the original cell complex, and then you do some modification on the boundary map, and then you inductively do this step, and eventually you will get to the Morse complex, which is actually a really brute force. In some way, this is probably quite a brute force algebraic way to do a proof. But I guess that highlights what I meant when I say, the geometric realization of some of the like the geometric realization of the Morse complex can be something that is a bit more complicated, can be a slightly more complicated matter, at least as from my perspective. But yeah, that's the end of my talk. So this is actually derived from my master thesis, which you can find in this link. And thank you, everyone, for joining my talk.
Okay, thank you very much, Chung-Ping. Any
Yes.
question from the audience? I have a follow-up question. So the picture we just looked at, which is the Morse complex of a simplicial complex, is not necessarily a simplicial complex. So what happens if you start from a simplicial set instead, right? So we can consider the Morse complex of a simplicial set because it's a abstract cell complex, as you mentioned. So is it going to be still a simplicial set, or is it going to be something more complicated when you? I guess in your example, it remains to be a simplicial set. No, if you just go back to the triangle example and look at the Morse complex, it will be a simplicial set, I think. Is there a connection problem?
Sorry, I couldn't hear you.
Oh, I see.
Are
Okay.
you speaking, Cihan?
Yes. Are you able to hear now?
Oh yeah. Okay, I can hear you now.
Okay.
Yeah.
So
Okay.
let me repeat. So I was asking as a follow-up, if maybe we can just go back to this triangle where you looked at the Morse complex of the triangle. So
Yes.
if you look at the Morse complex, this is like a simplicial set, right? So you have a
Yes.
single loop and then you glue a triangle. So it's a simplicial set. I was curious if you look at the Morse complex of a simplicial set, which we can think of like as an abstract cell complex, right? So does it remain to be a simplicial set, or do you start to see something more complicated that is not as simple?
You don't get to remain a simplicial set, unfortunately. So there's like this example. I will just draw it out, which you can see is so it would be it will look something like this. So this is an example by Forman, which I hope my drawing don't do him a disservice. But essentially, for example, if you start with a simplicial set like this, simplicial, I mean it's also a simplicial complex. What it can happen is that you can really turn this into you can really the Morse complex when you geometrically realize it really becomes something like this,
Okay.
where you have like a lot, so you have a face with like a lot of edges, which would not be a simplicial set. So the simplicial set, unfortunately the simplicial set condition can also be broken in the process of like stretching the Morse complex. So that's something that can happen, unfortunately. Um,
Yeah, they look
yeah.
more like cell complexes. So the inside is filled, right? So this is like a disk.
The inside is filled. Yes, the inside
Yeah,
is filled.
I see. Okay. Mhm.